Hello and welcome back. We've been talking about random variables, and today we'll start talking about some of their properties. In particular, we'll talk about expectation. So what matters about a random variable? You can ask what are different features of a random variable that we'll care about. So what would be the important things that we would like to know about them? And one example might be the range. Namely, we might be interested in what is the smallest value that a random variable can get, or what is the largest possible value that it can get. For example, we may wonder what is the lowest possible temperature in San Diego in January, and what is the highest possible temperature in January here. Or we can ask, if we want to join a company, we may wonder what is the lowest salary that they pay and what is the highest salary that they pay. Okay, and so the minimum value, we can just define it as the minimum of all elements in the sample space, all elements in omega that have positive probability. So just take the smallest of those. And the maximum, we can easily find it given the distribution function p. We can just look at all elements in the sample space and consider only those that have a positive probability and take the maximum of those. Okay, so these are easy to find. As we can see, they're just simple functions of the distribution function. Okay, we can also wonder about the average value. So for example, we may wonder what is the average temperature in January, or what is the average salary that the company pays. Now, once you start talking about average, you have different options of how you would define it. So let's look at a couple. First, you can look at the average range. So we know that the range of the variable is somewhere between x mean and x max. And we can just say the average is going to be just the average of these two extremes. So it's x mean plus x min plus x max over 2. So that's one option that we might choose. Another option is to take the average of all the elements that may happen. So for example, here we're taking all the elements that have positive probability and sum them up and divide by their number. So we'll just take the average of all elements, x with positive probability, just add them up, divide by their number. Okay, so let's see a couple of examples. So suppose that we have a distribution ranging from 0 to 100, and suppose that the probability of 0 is 0.8, the probability of 90 is 0.1, and the probability of 100 is also 0.1, or 10%. Notice that these probabilities sum to 1. And what that means is that every other element, for example, 1, 2, or 3, will have probability 0. Okay. Now, if we looked at the range average, the smallest element that has positive probability is 0. The highest element is 100. And so the average range is the average of these two numbers, which is just 50. Okay, so if we look at this random variable and look at the smallest and largest possible outcomes, the average is 50, so that's one possible definition. The other definition that we discussed is the average of the elements that are of positive probability. There are 3 of them, 0, 90, and 100. So we could just look at 0, 90, and 100 and divide by 3, and that will give us 63.3. Right. Now, but there's also a third way to look at averages. We could, for example, take 10 samples, and because of these probabilities, that 0 happens probability with 80% probability and 90 happens probability 10% and 100 probability 10%. If we took 10 samples, a reasonable outcome may be that we see 8 zeros, and 190 we see ones, is 100 appear once. And we could also take the average of these numbers that we see. Okay, so if we do that, then we'll get what's called the sample mean, because this is a sample of size 10 from the distribution. And what we need to do is we need to sum those elements and divide them by 10. So when we sum the element, we take 0 8 times. So 8 times 0 plus 90 appears once, plus 90, and plus 100 that appears once. And we add them up and divide by 10. And this gives us 190 divided by 10, which is 19. So we see that we have 3 different averages, so to speak, depending on the definition of average. Okay, and the one that turns out to be more important is actually this last one. So it's because it's more representative of what we'll observe. Because if we get samples from this distribution, well, first of all, 100 and 0 will appear with different probabilities, and there are some things in between that might appear that we care about. So this is not so representative. Also, the average element is not representative because 100 has very different probability from 0, and this one does not take it into account. The sample mean, on the other hand, is what we'll actually observe in practice, and that's what we care about. So this is what we want to figure out. What is the sample mean when we take a sample? And clearly, we don't want an answer for a sample of size 10, 11, 12. We want to see what would happen when the sample grows in size. So that's what we're going to do. So we want to see, look at the average, or it's also called the mean, of large samples. So let's consider a fair die first. And we roll the fair die n times, and this number n is going to be very large. Let's say it goes to infinity. And we ask, what is the average of the observed value that we get? So we look at each element that we observe n times and sum those n elements up, divide by n. We want to ask, what is that going to be? Okay. So because each face of the die has probability 1/6, so each value, each face will appear roughly n/6 times. So when we sum the elements up, then n/6 times will add 1, and another n/6 times will add 2, and so on, up to n/6 times will add 6. We'll have to sum those up, and when we do that, we'll get the sum of all the faces that we saw. We normalize by n, and that's going to be our answer. Now we see that n cancels here, and also the 6 we can move to the denominator. So what we'll get is just, so at the n cancel, the 6 move down, so we get 1 plus 2 plus 3 up to 6, divided by 6. Okay, and this is going to be just nothing but 1/6, and then what we have here is 1 plus 2 up to 6, which, as we've seen before a couple times, is 1 plus 6 times 6/2. The 6 cancels, and what we get is 7/2, which is 3.5. Okay, now, so what that tells us is that if we roll the die many times, then what we expect to see is that the average is going to concentrate around 3.5, which is very reasonable because we have values from 1 up to 6, and all of them are equal likely, so expect to see the average between 1 and 6, which is just 3.5. So this is very reasonable. Okay, let's look at another example. Suppose we take our 4-sided die that we have seen before. So it has 4 sides with probability 0.1, 0.2, 0.3, and 0.4. And you notice this probability sum to 1, as they should. So if we roll this die n times, and n is very large, then what we expect to see is we expect 0.1 times n, namely n/10 of the times, n/10 times, to see the value 1. And we expect 0.2n, or 20% of the time, to see 2, and 0.3n of the times we expect to see 3, and 0.4n of the time we expect to see 4. So, and you notice that these numbers also add up to n, as they should. So what is the average? So the average is going to be 0.1n of the time we see 1, we'll add those, and then 0.2n of the time we'll get 2, we're going to add those, and then add the 3s and add the 4s, and we divide by n, and again the n cancels. So what we get is 0.1 times 1 plus 0.2 times 2 plus 0.3 times 3 plus 0.4 times 4. And what is that? That's 0.1 plus 0.4, which is 0.5, plus 0.9, which is 1.4, plus 1.6, and that's going to be 3. So one thing to notice is that here, if we just took the average of 1 plus 2 plus 3 plus 4, we would just get 2.5, right? Because it's symmetric around 2.5. But in reality, if we flip this die, if we roll it many times, the average is not going to be 2.5, it's going to be 3. And the reason is that large numbers like 3 and 4 are more likely than small numbers like 1 and 2. So the average is moving from 2.5 to 3, right? So that leads us to the definition of the expectation. So if you repeat an experiment n times and n goes to infinity, then every value x will appear px times n times. So if you take every element x in your sample space in omega, then it will appear px times n, the probability of x times n times. Okay, so the mean, therefore, is going to be roughly what we call the expected value of x. It's roughly going to be the summation of p of x times n. That's how many times x appeared, and each time we add x, which is we multiply by the value of x. So every value x appears p of x times n times. We sum those values up, and then we divide by n, and that's going to be summation, the n cancels, summation of p of x times x, and that's what we are defined to be the expectation of x. So this is our definition of the expectation of x. It's just summation of p of x times x. So you notice that we took the motivation, which is the average that we'll see if we repeat the experiment n time, and we got that this average has a very simple formula that is just determined by the distribution p. It's just summation of all x in the sample space of p of x times x, and this we call the expected value of x. It's called the expectation. Okay, and another thing to note is that the expectation of x, this e of x, is not random. It's not something that that depends on the experiment you did. It's a function of just the distribution. It's a constant that is a property of the distribution, is determined by the distribution. If you give me a distribution, for example, if you have a die, each side has probability 1/6, I can tell you what is the expectation, which we'll calculate in a minute. And if you give me the four-sided die, I can determine the expectation. It's going to be just a fixed number, a constant, that does not depend on the experiment itself. So let's look at a couple of examples. Let's look at a fair die again. So what is the expected value of x? It's going to be, by our definition, it's going to be summation of I going from 1 up to 6 of the probability of I times I. But for a die, every side has probability 1/6. So it's going to be summation from I going from 1 up to 6 of 1/6 times I, which is 1/6 in the denominator, and then we need to add 1 plus 2 up to 6, and 1 plus 2 up to 6, as we know, is 1 plus 6 times 6/2, and the 6 cancel, and we get 7/2, which is 3.5, which is what we got before. In other words, beforehand, we said, okay, imagine that we roll this die many, many times, and we convinced ourselves that when we do that and we add those numbers, we're going to get 3.5. And what we see here is that if we use this formula, that the expectation of x is summation of pi times I, and we do not repeat the story about performing the experiment many, many times, we just calculate this formula, we get again 3.5. And it's not surprising because we derive this formula from the expectation. So this is what we would think would happen. I just want to observe it. Okay, let's look at the other example that we had, which is a four-sided die. So the expected value of x here is going to be the summation I going from 1 up to 4 of p of I, the probability of I times I. And in this case, it's going to be 0.1 times 1. That's the probability of 1, plus 0.2, the probability of 2 times 2, plus the probability of 3, which is 0.3 times 3, plus the probability of 4 times 4. Okay, and when we add those numbers up, we get 3, which again agrees with what we had before, again for the same reason. So again, we can just calculate this summation and get the expected value of x, which is what we expect to happen when we add the values that we see and we normalize them by n, and n is very large. Okay, so let's do one more example that we did not do before. So now we can just calculate the expectation directly. So let's say we toss a coin 3 times and let x be the number of heads, and we ask what is the expectation of x. So here is the experiment, and we've shown this before this experiment, but we didn't calculate the expectation. So x takes the value from 0 to 3 because we tossed the coin 3 times, so we can have anywhere between 0 and 3 heads. And we'll get 0 heads if the outcome is tails, 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 which happens probably 1/8. We'll get 1 heads if these are the outcomes, happens probably 3/8, and so on. And we ask what is the expected value of x. So the expected value of x is summation of p of x times x, which is x gets the value 0 of probability 1/8, so it's 1/8 times 0, plus x gets the value 1 with probability 3/8, as we see here, so it's plus 3/8 times 1, plus 2 times its probability, 2 times 0.38, plus 3 times 1/8, and when you add those up, you get 1.5. Okay, so what that tells us is that this calculation is the calculation of the expected value of x, and it's also going to be, if we repeat this experiment many times, namely we roll 3 dice once, we record the number of heads that we saw, we repeat the experiment again, we record that, and so on, and repeat it many, many times, then when we repeated this triple a large number of times, and we look at the average number of heads that we got, this average is going to be 1.5. All right. And it also makes sense because the number of heads ranges from 0 to 3 and a little bit symmetric, as we're going to talk about in a second. So the average between 0 and 3 is 1.5. All right, so that makes sense. All right, so I just want to make a couple of observations about the expectation of a random variable. So first of all, uniformity. If you have a uniform random variable, which means, as we know, that all the probabilities are equal, then the expected value is just the arithmetic average of the outcomes, because we have summation of P of x times x, but P of x, each P of x is just 1 over the number of possible values. So they'll just add to the same, you just divide by the number of values, so it's just the arithmetic value of the outcomes. So for example, if we had a fair die, then the arithmetic average was going to be 1 plus 2 plus 3 up to 6 divided by 6, which is 3.5, which is what we had before. And the reason is, again, because it's the same as saying 1 times 1 over 6 plus 2 times 1 over 6, and so on, up to 6 over 1 over 6 times 1 over 6. Okay, so this is just the expectation. The other comment is that if you have a distribution which is symmetric around some value a, which means that for all x, the probability of a plus x is the same as the probability of a minus x. And then if p is symmetric around a, like which we define here, then the expected value of x is going to be a. For example, if we look at the coins, then we see that this is the distribution of the number of heads. It's symmetric around 1.5. Probability of 1.5 plus 0.5. The probability of 2 is the same as the probability of 1. The probability of 0 is the same as the probability of 3. So it's a symmetric around 1.5. And if that's the case, then the average is going to be the center of symmetry, A. In this case, it's symmetric on 1.5. So the expected value is going to be 1.5. And that's because you get the same number of time you get 1.5 minus 0.5 is 1.5 plus 0.5, and these will cancel, and so on. Okay. All right. So, so in this lecture, we talked about expectation, and next lecture, we're going to talk about functions of variables. See you then.